So I'm going to talk about minimizing carbon in multifamily systems because, well, because that's what we've already been preparing to do for quite a few years now, and now we're just kind of taking it to the next level. We've been minimizing the energy use of buildings for, gosh, I don't even know, 15, 20 years. I don't know how long Passive House has been in this country, but it's been a while, and we've gotten a lot of stuff figured out, but there's always places for us to go. And I think that carbon accounting is our next kind of big unknown area. A couple of years ago it was dehumidification, then it was domestic hot water, and now it's carbon. So I also want to make a plug for getting out of your comfort zone and getting into other movements as well, because this is how we kind of multiply our impact. So that's CNUA. I don't know how many people are familiar with the Congress for New Urbanism, but it's all about creating walkable, lovable places, and we all know that where we build our buildings and what they're doing is just as important as how much energy they're using, because the energy that we're putting, the people that we're putting in the buildings is actually the most important thing. So let's make buildings that are loved, and let's make the places outside those buildings with the way that they shape space. Let's make it loved too. So now to get into to drill way down. So so I directed this large research project, and Matthew Fisher at my office would help me out with the using IESVE. And if any of you have used it before, it is a sprawling, crazy program that has a million little levers on it, and to make it do things right is quite a feat. But so we went through and we analyzed. There's four different mechanical systems, 5 different ventilation systems, and 5 different domestic hot water systems that we analyzed for the energy, and then for the embodied carbon of the systems and the refrigerant and everything we could put our hands on. Of course, there's some assumptions we made, and because we have to. At this point in time, we can't really account for everything embodied, because there's so many things that aren't being accounted for right now. We don't know how much carbon equivalent we're really using in all these pieces of equipment and all these materials. It's so hard to figure it out. But so we made a bunch of assumptions, and we used the ICE database and the GWP 20 numbers, and we used that stuff to get as close as we could. And so the analysis is done at a 20-year time frame, and for simplicity, it's a good life of most systems last at least 20 years, but they don't all last more than 20 years. So I thought it was a good life cycle to put on it. So all the numbers you'll see, well, the EUI numbers for energy use intensity are yearly numbers, but all of the carbon numbers are all for 20 years. So this building it's a really cool building. The existing building is a synagogue, and it's phenomenal. And they did a 3D scan of the interior of it, and they found that it's even more incredible than they thought. Like the way that there's intersecting circles going on in the architecture is just it's really, really cool. And that's being turned into a theater, but that's a long way off. The building actually, the apartment building is actually an L-shaped building. Behind, you can kind of see it in the picture, and behind it's 2 stories of new above 2 stories of old. And so there's a lot of carbon already captured in this building because it's an existing building. So I probably should give so it is a passive house building, and it's under construction. It's probably about 80% done, and it has although I saw Terrence on the call. Maybe he knows the more accurate number for that. But the building's 45 apartments and 57,000 square feet. And so on to the heating and cooling, and I'm just going to jump right into them. So the first system we analyzed was the heating and cooling was a variable refrigerant flow system. So this is VRF is the is the acronym. I'm gonna try to say all the real words, not just acronyms the whole time. So this is the system that's in the building. So we have every piece of equipment, all the ductwork, all the insulation, everything. We've got it all. We know exactly how much of it's in the building. So all these numbers are, the exact numbers. I'm not going to read them off or anything like that, but with VRF systems, the leak rate is higher for refrigerant because there's so much refrigerant piping, so many braze connections that, I mean, we've heard horror stories of the whole refrigerant charge leaking before the building even opens, stuff like that. So VRF definitely has a lot. I mean, 214 pounds of refrigerant is a lot. The second system is mini splits, and so we went through and we figured out exactly what the system would look like, and how much refrigerant piping was in it, how much refrigerant is in it, and the leak rate on a mini split system is a little bit less because each unit has only one line set. So, and if anything does leak, it's only in one system. So you have a little bit less leak rate and you have less than half the refrigerant in the piping. Geothermal, complicated system, not to be taken lightly, but the refrigerant all lives inside the heat pumps that are in each room. So you don't have any field brazing or anything like that. So the leak rates are lower and there's less refrigerant because it's all in a packaged piece of equipment. And then the darling of the hour, the all-in-one system. So this is like the EPOCA, which we get calls about EPOCAs every single day now. I don't know why they get it. I don't know how everybody gets our name, but everybody asks us how to use them. And Minutair is similar, but uses a different sort of idea to accomplish kind of the same thing. And they each have their strengths and weaknesses, but they use only a little bit of refrigerant, a lot like because it's all in a packaged system, so there's no split. It's super simple. There's just not much ductwork. There's a lot less stuff. And when you use one of these machines, because it just sits near near the exterior wall and has its louvers right outside. So it requires a little bit different architecture of the building, but you can get a lot of savings in cost too. Even though the unit's more expensive, all the installation's a lot less. But so their leak rate is low for refrigerant too. So here are the results. So I don't know if I said anything about the mental model yet, but creating those shortcuts in your head to kind of get you closer to the solution, not necessarily all the way there, but you always want to analyze this stuff. But it's good to know kind of the relative impacts. This is for this is in Pittsburgh, so it's kind of that in-between climate where there's a lot of cold days. The days get pretty cold, down to 2 degrees, less than 2 degrees, and so it's a mixed climate. There is cooling, but it's not as heavy as the heating. So some of these systems will perform better in warmer climates, and I'll go into that too. So VRF, it's good. It does well with energy. So on the left is the energy use intensity per year of these different systems for this specific building. So VRF does pretty well. Mini splits, they're still decent. I mean, all of these are decent systems. These all meet Passive House. They're all totally electric. It's just that the numbers are still very comparable to each other. It's not like one of them is like, oh, I don't want to use that because it's using so much energy. And also, here, there we go. That's perfect. So yeah, mini splits are, they're okay. Geothermal is really good with energy, and the EPOCAs are a little bit not quite as good with energy, but they're comparable with mini splits. But they don't have the super low temperature ratings that mini splits and VRF and geothermal have. Like they use electric heat below 5 degrees. So that's why actually you're seeing that. You see it actually in the red down there is the heating energy, and that's really where you're getting the hit, is from the electric resistance backup heat. And so the center is the 20-year carbon impact of and yeah, the numbers really don't matter, right? These numbers are all relative. Like the absolute numbers aren't the important thing here. They are when you go through and you do the analysis and then you put it into the whole building analysis. But for the mental model, the numbers aren't super important. It's more which ones are higher than others. But so the center graph is for a fairly dirty grid. This is Pittsburgh's grid. It's got a lot of coal in it and natural gas and things like that. And the one on the right is the grid just north. It's in New York. It's it's a much cleaner grid because they got a ton of wind because it's on the Great Lakes. So it's just they've got lots of wind and they're using it, and it's great. They're doing that, and the grids will all kind of head that way as more renewables get added. But you can see that the relative carbon impact changes as the grid gets cleaner because different things become more important, or they become more of the carbon pie. So VRF, it looks pretty good when you have a dirty grid because your operational carbon is the biggest piece of the pie. But as the grid gets cleaner, or you add solar batteries to your building, the refrigerant becomes more of an impact. So all of a sudden, when you have a clean grid, VRF starts looking pretty bad for carbon because of all the refrigerant that's leaking into the environment. So you can see that the trend actually changes. So you can see in the clean grid scenario, the all-in-one EPOCA unit actually does really well with carbon because it's using very little refrigerant because it's a packaged system. So yeah, so those are that's kind of, you can see. So the red is refrigerant and the yellow is operational, and the embodied of the actual machinery, which I almost forgot to mention, is the blue, because it's fairly low. The mechanical systems aren't that heavy, so they don't have a lot of embodied. There isn't a lot of embodied carbon in the actual machinery. It's mostly in the refrigerant and in the energy that they're using, which makes sense. I mean, we're powering the buildings, or we're conditioning the buildings. So, and also something I also want to mention about this is that in order to normalize this so that we're just analyzing heating and cooling, we took out the ventilation. Well, we made the ventilation all the same for these. So these are all the three systems, the VRF, mini splits, and geothermal, are all using a small room by room ERV that kind of because it's very similar in performance to the one that's in the all-in-one EPOCA system, because we try to normalize it all so that it's easy to see the actual differences. So on to, well, I probably already said all this stuff, but the reason that we chose VRF for this building was just that we couldn't really use geothermal. It just geothermal didn't make any sense for financial reasons, and it often doesn't for passive house multifamily. Like geothermal, it makes a lot more sense for kind of crazier buildings, like, I don't know, say a hospital or an off-grid wellness retreat, or the kind of wilder systems, or systems where energy is king. Like you have to reduce the energy as much as you can. Those are there isn't it. Financially, it doesn't really work. Geothermal doesn't usually work for multifamily buildings. And also with geothermals, you really got to be careful. You got to make sure you got someone really good to install that system, because it's underground, and if something's wrong with it, it's really bad because you just can't make it work right if it wasn't installed properly. So there are some people who do it really well, and so make sure you get one of those guys on your team, or girls. I don't know if there's any girls. I haven't met any. I haven't met any geothermal girls. Maybe that should be something that we work on. All right, dehumidification. So so I told you earlier that we split the we took the ventilation, we took the like essentials ventilation out, because that's really the real purpose of those systems in a putting a giant ERV on your roof, or energy recovery ventilator on your roof, is so that you can control the humidity at the ventilation air. So we got five different systems here, and this is the most common one. You see this one everywhere. We analyzed it for Trane, but Daikin, Greenhack, Aon, they all make the exact same thing, like almost exactly. They sit on the same curves and everything. So they are a package solution. So they're nice, but you're adding a lot of ductwork. You're adding ductwork, down chases, through hallways, and there's other ways to do this too. You can do it, floor by floor and little neighborhoods of them. But it's a package system, so it's the compressor and everything is all right in it. So you're not gonna get a lot of leakage from it. You don't have a whole lot of refrigerant in it, but you have a lot of extra ductwork for any central system. So the second system was we split apart the dedicated outside air system. Everybody's seen the Swigon. Everybody's talked to the Swigon people, and the Ventacity and those the fancier ERVs with the higher efficiencies. They don't have packaged versions of those yet. I don't know. Maybe they will. And but so you and oh, am I? He's trying to show me the time. No, okay. Okay, I'm just gonna keep going. Okay. All right, thanks. So we split apart the dedicated outside air system into two pieces. And so the usually like a VRF unit is, onto a DX coil that's attached to this unit. And it it does the dehumidification process using a VRF system. So there is some field installed stuff, so it's a little bit harder to install in the field, and there is the possibility of more leaks. It's not a lot more refrigerant, but it is a little bit more refrigerant. But these systems are really good at low temperature performance, whereas the package systems aren't quite as good. So as you get colder, these become better and better than the package systems. The third system is a geothermal system, packaged geothermal. So this has a lot of benefits of the first system, and it's for plugging into it. If you're already using geothermal for your heating and cooling, use it for dehumidification. And this is just another variation of that, where you split it apart. You use a really high performance ERV, and then use the geothermal water to water unit to and these systems, they perform really well. And then there's the wall mounted or room by room dehumidifiers, and these are simpler because they don't have any ductwork, so you're getting rid of a lot of the you just don't need all that ductwork through your ductwork, smoke dampers, all that crazy stuff. You can get rid of that and use if you're using like an EPOCA system, then you've really simplified your system. But as seen in this next graph, they aren't quite as efficient, because they're central systems are often have the benefit of using you get the economy of scale with a big unit, and you can get some really good efficiencies. So on the left is the energy use intensity of adding dehumidification for 1 year. So packaged dedicated outside air system, decent. The split system is better. About, in this climate, it was about 15% better, and most of that energy actually was in low temperature. Like none of it came from cooling at all. It's all in the defrost cycles, and because VRF doesn't, VRF can operate really low temperatures, whereas the packaged dedicated outside air systems can't really do that. So they rely on the electric heat a little bit more. Packaged geothermal does really good. Split is even better. And the wall dehumidifiers kind of coming in the middle. And that is because they're only treating the room. They're treating things at the, they're watching the humidity in the room. So they're just not dehumidifying quite as much. And so it's more about controls than it is about actual efficiency of the units. So even though they're a little less efficient because they're just a little tiny thing sitting in everybody's apartment, they get that benefit of, they're not dehumidifying when they don't have to, because a packaged system on the roof definitely does. It doesn't always, it can't always hit exactly the right spot. So when you're talking about carbon, in a dirty grid like Pittsburgh, it follows the operational energy pretty closely, and you don't really see any differences until you get to a really clean grid where you start to see the refrigerant popping into the pie a little bit more, and you start to see that the decisions you make about how much refrigerant you put in the system do have an impact, but you really can't see it until you get to a clean grid. So it kind of gets more pronounced, but you can see that the package dedicated outside air system actually ended up a little bit less carbon impact than the more efficient dedicated outside air system, which was a really interesting thing to see that refrigerant, the red refrigerant line kind of starting to be more pronounced. Oh yes, of course. Yellow is operational, red is refrigerant, and blue is embodied. And the embodied, they're all basically the same because they're central systems on the embodied side of the equipment, but except for the wall dehumidifiers, because there's just so much less ductwork. So there's so much less insulation, and you actually see a little bit there, but it's not the biggest thing. So yeah, I think I went all over all of this. The package dedicated outside air system was used because they are the cheapest and they're the simplest as well. If you don't need to have, the commissioning is very easy. All of that stuff is very easy. The roof penetrations are all easy, which is also good for passive house. So that's why we went with that for this building. And the EPOCAs didn't exist yet, so couldn't really use those yet. Because this was in design probably 5 years ago, so that does affect some of the things we did for this project. And to the new mainstream, I think we've gotten, so on domestic water heat pumps, I think we're starting to get into I think we're starting to get past early adopter and heading into early, oh man, I just blanked. The early majority. We're getting into the early majority because I've been hearing a bunch of people called me up and said, hey, they were talking about carbon dioxide refrigerant at Greenbuild. And I was like, yes, we've gotten past the early adopter phase. So that's great. So the first system we analyzed was distributed tanks, and these have been around for the longest time. Well, out of all the heat pumps, these have been around the longest. So this was actually the only system we actually had at the time to do heat pump hot water heating in for this building. But it's relatively simple because you don't have a circulation loop or anything like that. It's just a heat pump per 1 or 2 apartments, and it's a package unit. Doesn't use a ton of refrigerant, and doesn't leak a whole lot. So the first of the central systems is this one's kind of our personal favorite right now. We're doing a lot of these because oh, Swigon is not the right word there. That's a sand CO, that's the sand CO2 from Sandon. And these, I mean, Sandon was the first one to get the CO2 heat pumps to this country, and we thank them for it, because the CO2 really does a good job of heating hot water. It's a really good refrigerant for heating hot water. It has its limitations, and it has its little little quirks, but it does a really good job. So this is kind of the first system is kind of a hybrid system. So you use the Sandins to use the CO2 heat pumps to heat up the bulk of the hot water, because they want to see a really high delta T. What that means is they want to see 45-degree water coming in, and they want to see 140, 160 water coming out, which is very unusual for a heat pump, and that's why CO2 is kind of a fun refrigerant. Doesn't work very well for cooling at all, but for heating hot water, it's fantastic. So, so the limitation with the CO2 heat pumps is that they don't want to see the recirculation water. And when you use a central system, you need recirculation water. You can't just let the water get cold in those pipes. You need to move it around. They have smarter ones now where they actually like learn from the building. So that's pretty awesome. And so, we can minimize the energy of the recirculation loop. There's a bunch of strategies for that. That's a whole presentation in itself. But we have to heat that water back up, because that water comes back at 95, 100 degrees. We got to heat that back up to 120. And so the best way that we've found to do that is use one of these tank type heat pump water heaters, and just let that thing handle the recirculation load, and let the Sandins handle the bulk of the hot water heating. Let those different heat pumps do what they do best. And the other way to do it is not to use a heat pump for that recirculation load, and use electric resistance. And this is the system used that is like the standard Sandin system. This is going to be initially what Mitsubishi also recommends for their brand new system, and we're going to try and get them to use a heat pump in that for that recirculation load too. And I really apologize about putting Swigon in there, because that's not who it is. Central geothermal, another variation on the theme, but this is I mean, you're using your geothermal loop that you've already got from heating and cooling, and you add to it with your hot water. And that's pretty much how these work. There's a few moving parts in them, but not any more than this, not any more than any other central system. The most complicated and not well known system is using VRF to heat hot water, and there's actually a secondary compressor that heats the hot water, and you have a VRF compressor on the roof, and you have a secondary compressor down in your mechanical room that heats the hot water. And these systems are complicated. These are and not many manufacturers do it. Like Mitsubishi pulled theirs out of the American market, so they don't do it anymore. So there's only a few people that make it, and so it becomes tricky to manage that, because you don't want if you've got a VRF system on your building, you don't want to have two different VRF manufacturers. That's just nonsense. But these systems are a little bit complicated, and they're VRF, so they come with their refrigerant problems. They come with a lot more refrigerant, there's different refrigerants. So you get different. There's some limitations to this, and it doesn't do as good on energy anyway, because you have that secondary compressor. So all of these numbers are really good. I don't want to say that any of these systems are really a whole lot better than any others. In fact, it's hard to tell if any of them actually are. So if you look on the graph on the left for the energy use for a given year, they're all pretty much neck and neck. And the little differences are like, so the yellow is just the bulk hot water heating, and then the red is for the recirculation heating. So you can shave that off by using a heat pump, but these are all really good systems. These all perform really well. Even the VRF is not, it's not a terrible system by any stretch of the imagination, but it's yeah, so they're all really good. I don't want to discourage you from using any of these, but you can see the carbon impacts with the current grid are tracking along with the operational energy, just like they did in all the others. And you can, there's very little variance in all of them. And depending on how cold your climate is, will affect these a little bit more. So the colder you get, the more energy you're going to use for all the different systems. But certain ones will do better than others with the colder climates. And then when you get to a cleaner grid, you can, it really, these systems are all really evenly, they're all very good. So they're all doing well in refrigerant and in operational. So you can't really go wrong with heat pump hot water. That's pretty much the the takeaway from this. Oh, and I put this in right at the last second. So this is for 20 gallons per day, which is not the passive house standard. The passive house standard is 6.6 gallons per day per person. And so what we've found is that in like family buildings, people use a lot more than 6.6 gallons per day. But in senior buildings, they do use about 6.6 gallons per day. It's actually kind of when we actually measure it, it's kind of amazing that it's that low. I don't know where that number came from. I don't know if it came from Europe or from senior housing. It could have been either. So the refrigerant and the recirculation are just more pronounced when you use less water. You're recirculating the same amount, but it's a bigger piece of your energy pie. So I thought this was really cool to put this in, because you start to see the recirculation energy and how the different systems do on the recirculation energy, which is interesting to see. Carbon impacts, you can see them on the graphs. There's all the heat pumps still do really good. So I don't want to discourage any certain types. There's definitely a place for all these different types. And a lot of it has to do with your building. If you have enough room for distributed, that's a good type, but not all buildings have room. A lot of urban, like really, really dense urban buildings don't have room for distributed heat pumps. And you wouldn't want that many distributed heat pumps in a building anyway, because it's just a kind of a maintenance hassle. So central systems become a really nice option. Yeah, I already mentioned that the VRF is a bit complex, but it doesn't have any freeze protection issues, because there's a VRF unit on the roof that will never freeze. Whereas all the carbon dioxide based heat pumps they put actual water up onto the roof. So normally the freeze protection isn't an issue, because when the units are on, they are managing that themselves. But if you lose power, you got to be careful. So you have to provide ways of making it so those machines don't freeze up on the roof. And distributed tank type hot water heaters don't have that problem either. But you have to figure out how to duct them. You have to duct them to somewhere, because a mechanical closet doesn't have enough heating energy in it to because they're putting out a third of a ton of cooling when they're operating. So you have to find a place to put that. And and the warmer the climates go, that becomes easier. But so you have to either put it back into your ventilation area if you've got a central ventilation system, or you can put it into the rooms, which you get free cooling in the summertime, but you also get free cooling in the winter time, which isn't ideal. So so there's trade-offs, and you can see from the energy it doesn't affect it a lot, but each situation is going to be different for these. So that's it. I kind of rushed through, but bring on the questions.
So I'm going to hand it over to Scott and ask Scott, can you start with 1 or 2 questions tops, and then we'll come back?
Sorry, yeah, no, I don't need to monopolize, but I was curious whether you looked at heat pumps using hydronic distribution. We're trying to talk a client into that right now for a townhouse project. So central, well, yeah, and instead of using refrigerants, so, yeah.
Yes, actually we did look at it for this project when we were starting it. And it quickly was decided not, we quickly decided not to use it because it came out to about 20% extra. And part of that was probably because of the lack of for air to water heat pumps that we were able to use for our central plant, because we were set on electrification. So we couldn't use boilers, and 7 years ago, we couldn't figure out equipment to use it. And as far as the analysis goes on that, I'm pretty sure that hydronic comes out really well, as far as, I mean, it's certainly in their carbon impacts, but also in energy. It won't perform as well as geothermal, but it might get close because chillers have a really, really high coefficient of performance.
Yeah, so I mean, the system we're looking at using is space pack system in a parkade. It's Vancouver, so we're actually, the engineers won't let us put it in the parkade. They're making us put it on the roof. We keep saying we could probably put it in the parkade in a passive house, but they don't believe us, so they're making us put it on the roof. But it's not terribly cold, but the plan was to use hydronic. And most of the rest of my stuff was comments and, how do you model EPOCA? Because I've got a couple of projects we're citing those for, both passive house and non-passive house projects. And I have no idea how to model it in PHPP yet. So we're trying to find out if anybody's done that. Here up in Canada, it's still called the ANOVA, but it's the same unit. And the last thing, I would love to see a presentation on minimizing energy in your recirc loop. I would invite about 4 or 5 engineers to that, because this is a discussion I have. Anyway, thanks. Would you work in Vancouver? That's my last one.
I don't have a Canadian license.
Bummer.
We know some people, Chris. We can talk to a few people. We know some back alley things. We can get passports and a few things. We can get you up here.
Thanks, Sean. Our next question up is from Vaughn Piccolo. And Vaughn, I know you had a few questions. If you could keep it to 1 or 2, and we'll come back for the rest.
Oh yeah, sure. I didn't know I was going to talk here. I can pare it down to 2. I guess the first question was just about why it seems like you defaulted toward unitized ventilation systems. I guess as someone who's primarily working on affordable multifamily projects, generally sensitive to larger central equipment that's been historically more expensive from a first cost standpoint and from an ongoing maintenance and replacement standpoint. So I was just curious what decisions, what went into that for you? If that's your general default, why or why not?
That was actually to make the analysis be able to level the analysis for heating and cooling. Because if you centralize the ventilation, you're also dehumidifying. So, and it's a different type of system. So it wasn't comparing just the heating and cooling. So that the dehumidification kind of analyzed that. But you're right though, the central systems, if you use say just a central ERV and didn't have dehumidification in it, it would use more energy, and that was not something that I did the analysis on, was how much energy that uses just to make it a central system.
Okay, that's good.
I kind of combined it together. I kind of combined leaping to central and dehumidification at the same time. So that fan energy is in the dehumidification.
So then you touched on one of my other questions. So that's a bonus answer for me then. So I guess the second question is, in the unitized heat pump water heater scenario, where would you duct the rejected cold air, and where would you draw air in from?
So the big thing with those, the big problem with them is you don't want to create a cold spot. And you also don't want to introduce a lot of noise into the apartments or into just like some place in the hallway. So the intake, you know, if you have to silence it and use flex duct, the intake, we've taken it out of like closets and things like that to kind of mitigate the noise a little bit more. And then so there's kind of two systems that we've been using, and one is we send the exhaust air from the heat pump into the return of the room conditioning unit, or we have been putting it in, or we've been actually ducting the heat pump hot water heater just like a dehumidifier into the exhaust stream of the ventilation system.
Oh, cool.
That doesn't always work, but sometimes it does. And when you get into, you know, if you get into climates where you need to dehumidify and you need to cool down the outside air a lot, most of the year, if you go south far enough, it's going to kind of be a win-win for your dedicated outside air system.
Cool.
But it's a little challenging to get the airflows right. So you gotta that one's not for the faint at heart. ducting it to each room is the easiest way to do it.
Gotcha. Thank you.
Thanks, Vaughn. And our next question is from Rich. Rich, would you like to unmute? Looks like you're still with us, but I can ask your question for you if you don't have your audio available. So Rich wanted to know, is the Epoca like a compact unit from Europe? And I threw a comment in the chat, a couple other people did. I saw this last year at FIAS for the first time, the Italian unit, right?
Yep.
But they distribute out of Ohio, it looks like.
Yeah. And
for those who are unfamiliar with it, yeah, can you give us the lowdown on using it?
So there isn't a ton of them installed yet in this country, but they have promised that they can deliver as many as we need. So it is a big Italian company. So we're hoping that they can deliver on their promises, because we've had a lot of projects go that way, because especially because of the labor market's getting really tough, and a unitized system like those is really is really attractive.
So they self-distributing, or do they have a distributor in the US? And then what's the average price, roughly? Do we know? Or
I don't know if I'm allowed to say that.
Right.
Then you just say it depends. It depends, Kevin. It depends.
They're about twice as much as a mini split, but they contain an ERV and a mini split in one.
Gotcha.
And Eric Reinhardt, are you still with us? And would you like to ask your question?
Yeah, I'm here. I think I was intrigued by the percentage of refrigerant loss that Chris was showing on his comparative system graph. And I was wondering if you wanted to say a word about how one goes about calculating that.
That is actually, that's a really good question. And it's not super straightforward. There's not a lot of data out there for that yet. And so those numbers could be half. But it's that data, where did I get that from? So I think I used an ASHRAE paper, and I'd have to dig it up to find out where I got those numbers from. But yes, that's kind of infant level. We're right at the beginning of that. So those numbers probably will adjust as we actually get more data on that.
I'm good with that. I was pleased to have a presentation that showed the relative hit that we take with different system choices. So if it's still a black box, I'm okay. You can come back and explain it to us in more detail next time.
Yeah, there's going to be more data next time.
Hey, that's one thing this community loves, is more data. Can't go wrong with that.
Things get geeky, and they get geeky fast. John Burrell from Australia, are you having coffee? And would you like to come on before you have to go to work?
He's already at work. The guy doesn't he just continuously works. He's probably on his third cup of coffee.
He wants to know, a topic for the future could be geothermal, or have you done one before? Now, I know you covered this in your graphs and you talked about geothermal. So maybe I'll just tag on to this a little bit, Chris. When you're calculating the impact for geothermal, are you only looking at it from a systems perspective? Or are you also looking at it from the accounting in terms of moving earth and the other impacts?
So that is really different. The moving earth piece is really difficult. I could not find data on how much carbon is produced to drill a geothermal well. So that was not accounted for in the embodied carbon.
Yeah,
The wells
systems
themselves,
too.
like the
Yeah.
grouting the pipe, that was included, but not the
Okay.
actual drilling of the well.
Great, thank you. Appreciate that. I'm just impressed with how much you did account for, like I said. How about Derek? Derek, would you like to unmute and ask your question?
Hi all. Actually, I looked up my question and I got my answer because it just had to do with what's the wattage of a lot of these small fan coil units. My system uses 60 watts max, but boy, I tell you, once you add the heating elements in there, it's like 900 or 1,000 watts. So it's really a big load. But so I apologize. I didn't really have a good question other than I was hoping to see a lot more carbon data, and not specifically about the operating units, such as other embodied costs. And have you done larger studies with respect to all the rest of the MEP side of things for what's the impact of using some of these devices versus central units versus distributed units? Which ones were using, fewer materials?
Oh, there's not a graph for that, but that's actually in the, that's in each system's, each system had an analysis of how many pounds of equipment was in the system.
Mm-hmm. And did you cover all the other, MEP stuff, the electrical, things like that?
No. Electrical and plumbing. I did not account for the embodied carbon of electrical and plumbing.
Hmm.
Those systems are fairly similar. I mean, most of them are identical across all the different system types. These are just for the individual system, just that system's embodied carbon.
Right. I'll send you an email about that because a lot of people have been super interested because of the copper differences in what we do. We do a low voltage lighting system, and it's a tremendous amount of copper savings. And with copper being so expensive, big difference. But I agree with you. Most systems are relatively straightforward across the board.
Great
Thanks,
stuff
Derek.
there.
Thanks.
Shannon, you want to take over? So there's
Yeah,
more
thanks.
questions coming in. So we probably had more questions tonight than other things. So Chris, again, luckily these are going through fast, but we've got a list and it's still coming. So let's just keep going here. So now Gary Klein, don't you go too far because we're going to get to you in a second because we also want to know when we're getting part 3 of Gary Klein. And if you haven't seen part 1 and part 2 yet, you go back into the history of the accelerator because those are great topics that do talk about water management. And he's here today, which is great. But and again, Chris, it's really interesting because again, we haven't had this topic before, and I apologize that I missed it in Chicago because FIASCon, there's so much going on. And I, again, kind of knew some little birdie named Shannon told me that we were getting you on the accelerator. So I was picking and choosing my events, and this is so insightful. And even the questions here it's great. Andy, I didn't, again, I got carried away listening to the answers. I didn't check to see if Andy is Burnham. Where are you?
I'm here. My question was related to how the recirculation load was calculated relative to the primary water heating load. Just proportionally, it looked pretty small, and I was curious if there were efforts to optimize that or just what went into those calcs.
There's a lot to that. but yes, you do. We haven't measured that yet. So there's a lot of new stuff that's available, like all the circuits, all the thermostatic circuit solver valves for the end of the recirc loops, and the new learning pump controls. So we don't know exactly how they're operating, but like we kind of tuned, we kind of made a model kind of extrapolating the usage from the recirc loop to another building that we actually did measure, and kind of converted the number of risers to the number of risers that would have been on the central system for this building. And so we kind of extrapolated from another building.
Yeah, like I was just back checking based on like the EUI estimates. It looks like it was maybe 5-ish% of the primary heating load. Is that just generally in line? Like I've always been under the impression recirc losses can be quite a bit more than that. So I don't know.
They definitely can be. And there's that Gary would be the one to really give a talk about that, and how there is ways to optimize it. These numbers are for a very well controlled system. These are not for like using balancing valves and just using a constant volume pump. These are for like a sophisticatedly controlled system.
Awesome. Thanks for sharing. And great study. Thanks so much for all the data.
Sorry, Andy. And again, we're not like a Gary Klein answer that, because we want him to come back to talk with us, whole nother presentation, because we all know we need more Gary Klein in our life because of the insightfulness that he has. So Gary, you have to pause. You're not up yet. We have one more person before we get to you. And that is Mr. David Solomon. What's going on? You got a couple questions. I think we have you as 2 questions, but you might have 3 or 4.
Hey, great to see everybody. Great talk. Thank you, Chris. So you had mentioned that in order to deal with the recirculated hot water, you were pairing a regular unitized heat pump with the Sandin, because the Sandin didn't like the, I guess maybe the preheated water. And my impression was that regular hot water heat pumps, the unitized kind like the Reams and A.O. Smith and stuff, also didn't like or work well with that preheated recirculated water. And so is that a myth? Do I misunderstand that? Do they just not like it less than the Sandin? And just kind of what's your experience with ganging up or utilizing the hot water heat pumps within a recirculated system?
So the delta T, the change in temperature for an R410A or an R134A is much lower than for CO2. So they operate more efficiently, and they're a little bit more. So what we've been getting from Sandin and from Mitsubishi is that we'll void the warranty if we try to use their CO2 heat pump to handle the recirculation loop water. So we don't know exactly why that is. I mean, it takes a massive the coefficient of performance takes a massive hit when you put in warmer water into the Sandins. You don't get. I mean, it's getting close to 1 on the COP when the temperature differential isn't very high. So so it doesn't make it doesn't you might as well just use an electric tank. So I don't exactly know we haven't analyzed the exact reasons for all of that and the exact implications on the total COP of the system.
And are you seeing a COP drop with like a Ream as well? Is it just less of one, or?
So the thing is, those have a tank attached to them, and I think they're normally operating at kind of a low delta T, because they're optimized for a residence, which you use a little bit of hot water and the tank goes down to maybe 105 degrees and then it boosts it back up to 120. So it's operating pretty much, I mean, the recirc water is usually like 100, which is actually probably a little lower than it normally gets, but then it's mixing in the tank. So it's kind of a similar, it's doing a similar thing to what it's normally meant to do. So it's operating probably at a COP of 3 or something, you know, in that range. So they do well. You have to figure out how to get rid of that cooling or use it somewhere else. But
Right. Okay. That's helpful. My other question was, and a bunch of people, which I'm very grateful to, commented on this question in the comments, but I'll ask you as well. Do you have any recommendations for basically, I guess, an air to water heat pump that would utilize glycol for a radiant floor system?
oh, for radiant floors,
Yeah. So we
that's a-
have one. Basically, we
so-
have one at work. It's right now. It's you know, we use a gas fired boiler. We'd like to we want to completely get rid of gas. You know, phase it. That's the only thing that we use it for in our office, and we'd like to transition that existing system to electric, and so some sort of heat pump.
It depends on the size, what you want. Chiltrix makes a small one. There's there's actually a whole bunch of them that make small ones, and I'm blanking on some of the names. Arctic, I think, and several others. And then there's the bigger ones you'll see made by Samsung, and they're basically a VRF machine that's making hot water. It's an air to water VRF machine, pretty much. And
Okay, sounds like it's not. Is there any difference in those systems because they use glycol, or are they just a standard air to water system?
CO2 heat pumps, none of the CO2 heat pumps that we currently have are allowed to use glycol outside yet. We believe, and we can all ask Mitsubishi this in the next talk, because we think that Mitsubishi might allow glycol in the outdoor unit. However, that unit is a lot bigger than the Sandins, so it's different. It's operating for it's doing a different type of it's operating for a different type of building. And
Gotcha.
and I don't know if people use Sandins for radiant heat. I've seen it on their website that it's possible, but I've never tried it, and I don't know anybody who has. So it makes hot water. So you probably just want to be careful about how long it's running per day, because their Sandins are not designed to run all day long.
Okay. Yeah, and this is a well, I don't know if the Sandin would work anyway for us, just because of how the system is set up and like where our mechanical room is. And I know there's some limitations on the line length between the outdoor and the indoor unit. But anyway, I will do some more research, and I appreciate your advice. So thank you.
Yeah, Dave, and just a comment too is I know that in your market, especially in the Northeast, there has been a few of the Sandins that have done some hot water radiant floor systems. But I agree, Chris, is just again trying to unfold it like on all day long. You're pushing machine to do a bit more than you're wanting to, but because you're just trying to get a little bit more heat to help out with the floor, and you've got a bit of excess, and sometimes your recircs, you can do it. And it's funny, I agree with Mark. Like Michael knows this answers. Where's Michael? But I think he's on mute at the moment, but yeah, interesting things is just check with Sandin about what their limitations are, because I know our good friend Albert from Small Planet has definitely tried to push the Sandins further and farther than they were designed to, and sometimes you can do cool things with them. You just have to know the full limitations and the risks.
Okay, great. Thanks, Sean.
Thank you, David. And I saw us in the chat. Andrew Peel had a couple of comments there too. But our next question is from Gary Klein. Gary, welcome. Good to see you.
Hello, everyone. Good to be seen. Happy New Year. It's been a while.
Happy New Year.
Well, I don't think I've seen you since January, so we get to call Happy New Year. My question was about actually using, has anyone actually done a heat exchanger so that you could run a glycol unit out to a Sandin? My suspicion is that the working fluid and the working pressures change if the water is different than water, right? If the fluid isn't quite like water, then the heat pump has to work harder, which is why I suppose they get really annoyed if you use it as a for a recirc return, because I think that the operating system pressures go way up when the delta T's get very small. And I think that's the fundamental problem, is that's why you're making the unit work too hard. They don't want that. But my question, has anybody tried it? And I have a friend in New York who's willing to try it. He has a unit off of warranty. Let's see what it does to kill it, you know? I've got to find out, because this question of what to do about putting heat pumps with water in them outside keeps coming up. We get freezing in Sacramento, but not very much, right? But it's that once that'll get you, right? It's not the very much. Anyhow, I'm going to stop with my question and comment that, yes, we need to do a third or fourth or fifth version. I think we need to talk about research for both big and small buildings. Circulation loops are a really annoying problem, because we insist upon building buildings where the water heater is too far from the water's use to make it short. And so we have to figure out how to make it happen. So let's continue that conversation.
Thank you, Gary.
That's
We
it
will
for my
take you up
question.
on that for
Yeah.
sure.
And I know that our people are talking to your people, so just make sure your people will respond back to our people and we get all those fun connections. So keep those connections flowing.
I'll do my best. Scott has permission to bug me. I've been a little frantic this year. I apologize, but it is what it is.
It's
Well,
nice
so
to be
fit when you're
popular.
good. It's it. Absolutely. Yeah.
So Chris,
Thanks.
what do you think of Gary's question?
Oh, well, thank you, Gary. Yes, we do need to figure out hot water. What was the question in there?
Putting glycol in instead of water, and the experiment his friend is willing to try. Has anyone tried it? I think.
I don't know if anyone's tried it, but I do know that Mitsubishi is looking into it. So we're hoping for that, because that's a really big machine. So we want it to make it protected.
Excellent. Thank you. And next we have Salvatore. Or is it Salvatore?
It's Salvatore.
Welcome.
Welcome. Thank you. So, I've always envisioned the kind of the perfect heat pump scenario is where we reduce refrigerants almost entirely, and eliminate them as we understand it and know it, going to the indoor units. And we can have, in a typical residential project that has somewhere between 4 and 6 zones, a lot of refrigerant that scatters throughout the house to these indoor heads that are either low static or medium static heads, usually typically ducted. I think that what I struggle with is that I don't understand why the industry, this is probably less of a technical question, more of a cultural question on maybe what the group and feels as a whole, and Chris, why our easy go-to method to distribute chilled fluid and warm fluid instead of refrigerant, just distributing water and only relegating the refrigerant system from an outdoor unit to an indoor unit that distributes. It goes from refrigerant to water with a refrigerant to water heat exchanger on the indoor, and then distribute from there.
Right.
So you eliminate the glycol altogether.
I like the way you think.
So, eliminating the glycol altogether and just distributing chilled water and warm water to low static or medium static units, having minimal ductwork, and then having the ability to use areas in either radiant panels, using air, inline dehumidification. Why aren't we doing that more? Why are we messing around with these complicated refrigerant systems? And
is that what the Dakin Altherma system was trying to do, or I know they're not.
I think
anymore.
so. I think so.
So there's definitely some rumblings about it's kind of like a VRF hydronic hybrid, and there are some rumblings of that equipment on the near horizon, which would make the beauty of the beauty of the mini splits and the VRF and things like that is their controls are packaged and they just do everything for you, and you don't have to have a complicated control system for the building. And so I think that is how they have sold so many and have become the kind of the dominant force. So the air to air heat pumps basically. And I think it all has to do with the ease of installing it and ease of controlling it, because hydronics were the thing, 30 years ago. That's what everybody used. Everybody used water to heat and cool, and they fell out of favor. I think that a lot of contractors switched over to refrigerant, or they weren't training, or it's a I think it's more of a historical problem than it is anything else. And so it's hard in some labor markets. We can't, like the hydronics, they're just like, oh, that's an extra 20%. They don't even look at the drawings. They're just like, oh, that's going to be a lot more expensive to do that in this market. But there is some markets where they still do a lot of water, and like New York City still does a lot of hydronics. So it won't be as much of a premium in a place like that. And so it might be worth trying again. And it would be worth trying again. Like hydronics have a lot more flexibility. You can do anything with them. I mean, they're just coils of water in them. It's super simple. It goes back to your like actual engineering degree. It's not voodoo science. VRF seems like a sophisticated computer system compared to hydronics, where it's the plant is where all the sophistication happens. Everything else, it's all simple. So yes, I would like to see more of that, and we try to do that actually on this project. We tried to do that at the beginning and kind of got shot down. And we definitely need to do some more research into the best in class air to water heat pumps that we have now, because I'll bet you it's a lot different than it was 10 years ago.
Chris, great point. And just as we're talking big picture, the ability to provide like small amounts of heating and cooling at the ventilation point, I think is like what the original passive house was designed for, to eliminate the major heating and cooling major components, the hydronic units and the big refrigerations. So if we can somehow come up with a system that was that decentralized system that was able to provide a little bit of heating and cooling at the ventilation point, and we can insulate and air seal our buildings to where our heat load can handle that 3.14 kilobTUs per square foot or so, I think that would really be like an amazing system. I just don't know how we get there or who we follow to get down that path. But those engineers and putting in the work, I think somebody like you, Chris, and other people out there that can help us get there. On the other side, the insulation and the air sealing side, we just don't go to 3.14 for the heating load because there's no reason to, because we can hit it with traditional systems. But I think if you gave us a system where we could super insulate a little more and chase down a few more thermal bridges, I think we can get to that next level if we had a system or the engineering support to provide that little bit of that small little thing. That's my soapbox.
Well, and I think, Kevin, you make a good point with your questions. And then I think we should just open the floor up a little bit, because that philosophical question, there's a lot to unpack there, right? There's that thermal storage, there's load shifting, and a lot of potential. But David, you had a comment. Did you want to jump on again?
Sure. Thanks, Shannon. Yeah, my question was about thermal storage specifically, and companies like SunAmp and Harvest Thermal. And I was curious what your experience is of them, if you've used them. I'm starting to, see more talk and at least kind of advertising and education around them. I haven't used them yet, but I'm pretty intrigued by them.
Yeah, we haven't used those systems yet. We have been starting to look into them, but we have not used them yet.
Do you have any thoughts or opinions about them yet?
Not yet.
Not yet. Okay.
Yeah,
There
I
was
got
a session at BSCon, guys,
it's
where
apples to oranges.
Mhm.
there was a great session at BSCon. The climate lent itself to the thermal storage because there wasn't the issue of freezing and the volume that it takes to store water, right? But they did use I think they used the SunAmp system, David,
Mhm.
and they also did district energy with it. It was Jonathan Bean was his presentation, so I can follow up and throw a link in the
Okay.
chat maybe to that.
That'd be great, Shannon. Thanks.
But yes, thermal storage is we're going to be hearing more about that as more renewables get on the grid. Absolutely.
I wanted to follow up before I forget, Chris. There's a buddy of mine that does geo, and he does it inside of the building envelope with an all electric drill rig before the slab is put down. And that ground source is pretty good. And so because it's not where everything is to and from, right, in the quads of these commercial buildings and whatnot, plus all the routing back and forth, he's able to deliver enough hot water in addition to take care of both the domestic and the pool in these commercial entities. So it's definitely, there it is. Yep, rig in a box. You won't get him on the phone, but brilliant guy. All electric too.
This other thing. Oh, yeah. There's another thing that's interesting about the interrelationship between passive house and geothermal. It's very interesting to see because the geothermal becomes less attractive economically as you lower the loads down really far, but the balance point shifts. So you can put things like pools and you can put things like domestic water on it and use even less, you can be more economic with your wells. So it's interesting to see it, and we don't see it all that often, especially in multifamily, but the geothermal interplay is interesting.
It's kind of like, it's the conversation Doug Farr put out years ago. Add these things to your bid system. Just add the solar to the bid, add the geo, so that we're pushing the pipeline to be inclusive of these things. We all know things are going to get knocked off the bid anyway, but if we have this much more drive to it, now at least we're not 6 years from now saying, why didn't we try that then? Because Reed had a comment early on here tonight, and it was based off of the different grid uses later on. And I think that's the fun of this. Everything you said today, I didn't compliment it really earlier. Everything you said today was so amazing, and the questions and the diverse interest of the crowd, Chris, is why this topic is so awesome. Thank you for delivering it.
Thanks.
And I just dropped those links in the chat to the example I mentioned from the University of Arizona. I don't know if those were recorded or not, but for anyone interested, we're going to have Jonathan on the accelerator to go over that project. I'm really interested in it. I think water batteries are the bomb. So.
Well, remember Shannon, when we were in Chicago, we're looking at those couple of buildings that are using water as the sway well. What was that crazy word that we learned that I'd have to even look at? It's three things got to put together. I'll look it up. I took
inertia.
Global thermonuclear war.
Yeah, no. Good try, Mark. Thanks for No, I'm going to look it up. But anyhow, again,
thing, or basically there's so much sway because the building's so tall that it can create a sine curve it'll pull itself apart in the wind. So they put water in the upper floors to dampen that inertia, or to create inertia. And I thought, oh, well, that's inside the thermal envelope, so that's a water battery. No, it can't power the whole building, but could offset something, right? So anyway.
When you're on an architectural tour and people like Shannon beside you, they're always thinking inside the box and outside the box. So
is an inertial damper using the cistern at high floor levels. Was that it?
Yeah.
Interesting.
No, if it's using a cistern or it is a cistern, but yeah, it's,
You could. No, no.
I don't know how if it's ganged together, if it's one giant, I have to do some more research, yeah.
Probably-
Don't
Ask
know
Peter
yet.
Molinar, he'll have the facts for us before we're ready.
Yeah, I was gonna say, it's probably like those nice water bed, the water
Oh,
bed. came
Hold
out
on,
with-
again, sorry, this is why you take notes. Inertial slosh dampers. Yeah.
Thank you, thank you. And I will say that we lost Michael from Bethlehem earlier tonight. He must have had to go do something important, but he actually designed a water battery for like a 2,000 square foot house. And he did it by ganging 3 very small cisterns together that you can basically get from Home Depot and get through your doorways and all that. But it has to be a passive house. The loads have to be really low. So, all right, I'm going to go through the chat again and see if I missed anyone's questions. If I missed your question, please let me know. But in the interest of keeping my promise, I'd love to return back to Scott Kennedy if he's still here and see if he has any more questions. Scott, are you still there?
I am. I was just interested in your analysis, whether you looked at the difference between the Minutair energy use and the Innova energy use, given that the Minutair has to run its compressor all the time to do the ventilation part, whereas the Innova has a counterflow core, but we don't know how efficient it actually is. And that's some of the information I'm looking for, but I was wondering if you had looked at those things at all.
Yes, we have. Well, we haven't pitted the Innova versus the Minutair directly against each other, and it's very dependent on the climate, because the Minutair's low temperature performance isn't very good because it doesn't have an inverter compressor in it. And correct me if I'm wrong, I don't know if they've changed that, but we analyzed it a few years back. And so the low, it relies on electric heat a little bit more than the Innova does, just from kind of comparing the numbers, but they weren't exactly in the same places. The thing that's cool about the Minutair is that it does dehumidification. You can get rid of that wall-mounted dehumidifier that you need with the Innova. And so that's where it's kind of cool, is that it's only one piece of equipment that does everything. It's a small piece of equipment though. So like, for bigger apartments, neither one are ideal for bigger apartments. They're great for 1 bedrooms and sometimes for 2 bedrooms. But when you get to bigger apartments, neither one of them are ideal for that.
We're actually putting the Minutair in a 3-bedroom townhouse is what we're doing. So, and it's a passive house. So it's a international passive house. So probably a little bit more efficient than a Fiat one. It's a bit of a struggle trying to get it there, I must say, but it's under construction now. But I'm looking at the Innova on another passive house project. We're doing another 12 units here in Vancouver. So fortunately, we got a fairly mild climate in the winter here. It's not really cold. But I mean, the Minutair guy was saying, oh yeah, we got them in Alaska. But what you're telling me, they're going to do a whole lot of good up there.
Well, you're just going to have to heat up you just have to heat up the ventilation air up to a point that it can handle,
right?
Which I think is around 5 degrees Fahrenheit.
Does it have a preheater, a post-heater, or both?
I believe it's a preheater.
I thought it was a post.
I actually, don't quote me on that. Don't quote me on
no,
that.
I think it's a post heater. Actually, I think it's a post heater. That's yeah. Anyways, we had a presentation of the small Swigon units that are just available now. So you get a wheel instead of a core in a unit that's the size for a house. And that would have, to me, some big benefits in the cold climates. So that's something I'm interested in. We just saw them last week here in the office. So yeah. Anyways, thanks. Great presentation. I probably have a million other questions, but I got to go. So thanks very much. Good.
Thanks.
Thanks, Scott. Great to see you.
And hopefully, Scott, you got Chris's contact info, because I'm sure you guys can continue those conversations, because really insightful stuff.
I know where I can get it, Sean.
Thanks, Scott. Have a great night. Next question's from Andrew Peel. Andrew, you're still with us, right?
Yeah, I don't. I have technical issues. So I don't know if my video and audio.
You're there. We hear you. Yes.
Okay, good. Yeah. Awesome. Yeah. Great presentation. As Scott said, we could probably talk for hours about this stuff. On the geothermal side, we used to write it off because we'd always see projects and the cost would come out, just extraordinary. We're like, this doesn't make sense, right? And things have maybe improved cost wise over the years, or not. But what we've found when we've started to dig deeper, when we've been prompted more, like, well, why don't you seriously consider geothermal? Is and we look at it further, it's like, yeah, these systems are being oversized. We kind of treat it as a black box, like, oh, let the geothermal engineer do their thing. We get the cost back, and they size as they see fit. But when we kind of dig deeper into it, we're like, well, no, they're oversizing these systems, right? And obviously every foot, 100 foot or whatever of pipe is quite expensive. So I was wondering if you've done any work. I don't know if, I presume you guys don't do the geothermal design, like the loop side, but do you really work very closely with the engineer doing the design to really optimize for the loads of your passive house projects?
Yes. Yeah, you definitely want to work in concert. If they don't know how to work in concert with you, then you probably don't have the rock star you need. But they need things like the load profile over the year and things like that to actually size it properly. So if you just tell them your loads or your average, if you tell the geothermal the loop side engineer, if all they want to know is your maximum load and your average load, then you're not going to get what you need out of the analysis. There's lots of programs out there that run the loop, that analyze the actual loop. And the thing is, it's so sensitive to the soil conditions or the rock conditions or whatever is under the ground. It's so sensitive to those variations that's why they're probably usually oversized just to be safe, because they don't necessarily know what the thermal conductivity is. They drill a well in one spot, and they probably don't feel very confident about how that represents the rest of the site. And so I think that's where some of the oversizing is coming from. But if someone just says, oh, 2 tons per well, then obviously they're going to end up with something that's oversized. That's kind of voodoo science, I think. Geothermal well sizing. But I don't know that there's actually I was talking with the guy who does electric soil testing, and maybe that's something that could be used to kind of make geothermal the geothermal loop field engineering more robust, to actually get some scientific data on what the soils are actually doing underneath the ground.
Right. So you said electric field testing. So there's a approach where you can go across the entire site and get a sense of the soil or ground makeup.
Yeah, they have their it's not ground penetrating radar. It's the other one. It's like an electric field that they just pull it across the ground, and it shows the profile of the electrical profile, which they can I think that they can come out of that and deduce like things like thermal conductivity and things like that. It's I don't know if it's like an exact science yet, but it'd be interesting to see if there is a future for that marriage of those two technologies. It'd be interesting to see.
Yeah, that is interesting to see. I agree with you, because some of those don't yield much, especially when you've got a lot of rocks. Salvatore, did you have more questions that you wanted to share? I know you had a few earlier. I didn't want to cut you short.
No, I think I just wanted to analyze the group a little bit about the idea of carried the discussion about removing refrigerants altogether.
Yeah.
Trying to, yeah, I think it's, you know, it'd be beautiful to take the technology and the variable refrigerant flow modulating condensers and using that in a water to refrigerant heat exchanger on the inside of the house in order in just a strict effort to eliminate the glycol, because otherwise you'd have to bring glycol to the exterior. So eliminating glycol altogether, going to a refrigerant to water on the inside of the house. And there's one local company that I know does it. I've never worked with them, that has an interior heat exchanger that works with what's conceivably a variable speed outdoor unit that they attach to like a Bosch. And then once you have water and just traveling around the house with 5/8 inch or 1/2 inch or 3/4, depending on the side, typically 5/8 inch tubing to individual air handlers that are operating on an actuator. It can't get any simpler than that. I mean, it's beautiful. It's simple, eliminates refrigerant, opening and closing a zone and having very many zones, and an air handler with a water coil. Like I said, low static, medium static, very little ductwork. You can have many of them. I think it should be less expensive. It really, when you think about the component aspect of the material and the labor, should be less expensive because you eliminate the use of the technicals required from a refrigerant system in such a large typical VRF setup.
Is the issue space?
It's discouraging that it seems like we're diving into the more complicated when we should stick with the simple, because the heat capacity of water is immense, and we're just not utilizing it enough. And we're people who don't want to see wall-mounted units have to still relegate themselves to ducts, and you can really eliminate a vast majority of the ductwork by having zones individually serviced by really quiet fan coil units with water.
Well, that brings up a whole lot of questions for me, because I agree with you. I would love to see this technology. One, is it space-based? Is it just because water takes up so much room? And have you guys seen the
Takes up less room than air.
Yeah, less room.
I just mean the thermal storage of the thermal mass, but
like a buffer tank, you mean?
Yeah, like the buffer tanks, or how many do you need?
Typical home could be, a typical home doesn't need any more than a 50-gallon buffer tank, and I think even less if you can modulate the outdoor unit.
It's the controls. Personally, I think it's the controls, and then being able to control it all and have reliable, consistent heat and cooling. I think that's kind of like one of the things that Chris mentioned, was why the split systems were so easily sold and got to the market as is, because they kept it simple, stupid. But we're adding it to very complex houses, but it's not really complex. It's really stupid. It's super insulated house, super air sealed. Everything becomes a lot easier and smaller. It's just
you mean simpler on a hydronic aspect, or simpler on a variable, a VRF setup?
I mean, simpler on a mechanical whole sized aspect, meaning instead of needing 100,000 BTU boiler to heat a house, we need 36,000 BTUs to do a split system. And then and then we get a ERV and a domestic hot water system. Whereas I think there could be some synergies in our systems if we could engineer it a little more and engage people like Chris that are more on the like the design development side and helping the manufacturers to that next level. But I don't think we're really there yet. But the origin story of Passive House was to design a house without an active system, and that heating load number of like Passive House International design of 3.14 is the ability to deliver comfortable air in the medium climate of Eastern, of Europe, without having to have a major boiler, and you can
Yeah,
deliver it through the air.
I think that in Dernstadt, that was the initial offspring where all of the heating and cooling loads are handled through the ventilation system. And when you have a hydronic setup, you can distribute it to many different places, and you can send it to an inline fan coil, preheating ventilation air, and also heating in our climate zone, in climate zone number 5, at least where we are. We can handle that 60 to 70% of the loads on the year. 30% will need that extra supplement. And actuators in a typical floor heating system has been used for, forever. Opening and closing an actuator, dealing with sensible loads is simple. It just gets a little bit more, it's a little different when we're trying to cool and dehumidify, and we're dealing with the latent loads, which can be handled with an inline chilled coil in our ventilation system. Most of our loads in a passive house from a humidity standpoint is coming from ventilation.
That's Salvatore, I think. And by the way, I'd love to work with you on this if you're starting to work with some hydronics people. But the two things you mentioned, one of them is dehumidification issues, and the other is that it's very easy to build a system from multiple vendors. And I think part of this might be that the vendors are trying to take control of the entire package as opposed to splitting it off. Because I used to see that a lot. You'd have one person doing the chillers, one person doing the distribution side, and companies wanting to compete for each piece of margin on projects. But the latent heat is an issue. The dehumidification definitely an issue. But there's other ways to solve that now. So, Peltier junctions, for example, do an amazing job of extracting water, moisture out of the air. So I think you're definitely onto something. That's why I said I'd love to work with it on the control side of things, because that's what we're doing next is a controls platform.
That's great. Love to chat. Yeah.
Yeah, get there into the private PM in the chat and share your contact info, and then come back on and share the rest with us. And Chris, I bet you'd love to be a fly on the wall for that. Well, Chris, I don't think we have any more questions, and the banter is great. I'm thrilled if you can stay, if more people want to keep chatting, but you spent a lot of time with us tonight. How are you feeling? Do you need to take off, or?
I can stay for a few more minutes. I can stay for a few.
I want to
Anyone else want to unmute and jump in and ask a question of Chris?
I just want to encourage everyone when this goes live on Thursday or Friday to take the link again, pop it on your media and network channels, and tag Chris. The more you share this with people, the easier it is. Not everyone's going to land on the YouTube or the accelerator. So pump it out, knock people over the head if you got to.
I think we're supposed to toast Chris, aren't we? Are we supposed to do that?
Oh, we are certainly supposed to toast Chris.
Long overdue. Cheers, Chris. Thanks so much.
People say it's bad luck to toast with water, but this is one of the most precious resources we have. So
H2O.
I'm calling it a compliment.
I have a question. I have a question,
ahead.
Chris. If I can.
Oh, yes, please. Enrique, welcome. Great
Thank you.
presentation at FIAS, by the way. If anyone else saw Diverse Voices, Enrique did a recording that was absolutely brilliant.
Thank you. Chris, we're using the Minotaur for just dehumidification and cooling in a tropical, hot and humid climate. So the reason I decided to go with the Minotaur is because it can provide the good size dehumidification capacity. The other choice was doing like an ERV with a DX coil, which was very complicated because you had more equipment there, plus a dehumidifier. So the Minotaur combines the ERV with the DX coil and dehumidifier in one, but we are using it for 1,000 square feet multifamily, 4 rooms, 4 bedrooms, house. So we will probably need also a mini split for additional sensible heat. But I think, I mean, because the way the minotaur is going to dehumidify, it's not enough for the 85 Fahrenheit dew points that we have there. So, but I think that probably will. I was wondering why you said that the unit is only good for like 1 or 2 rooms.
Oh, in Pittsburgh.
Okay.
It's the heating load.
It's because of the heating.
Yeah, because you have, when you get really low temperatures, you're relying on the electric heat. So you need to have enough electric heat to do that. So yeah, no tropical climates are like, I don't know if Minotaur is marketing down south, but
no, it's a first experiment. So we'll see.
I think it's, I mean, for the technology that they're using, it's actually an ideal fit because I mean the efficiency of an ERV isn't as important as in cooling as it is in heating, and you know it's so the fact that it's using it's actively it's using the evaporator coil. It's using it active. It's doing an active energy recovery that actually works to your benefit when you're always trying to get rid of latent, because it's a sensible only device.
Yeah. Yeah, they improved the humidification capacity too with the new version. That's why I didn't consider it originally, but with the new humidification capacity, it's much better now.
Yeah, I think that's actually, I think that hot and humid climates are actually a really good use for that technology.
Yeah. Okay. Thank you.
Thanks, Enrique. And Vaughn, what, you want to come back on? I know you had another question in here.
Oh yeah, sure. It seemed like the dehumidification systems that you showed were sized only for dehumidification, not also to provide ventilation. So just wondering how does the central DOAS system actually work from like a controls or distribution standpoint? Is there humidistats in each apartment that connect to it, or I'm just curious how that works?
Oh no, it operates on a discharge, and it's doing ventilation and dehumidification is what it's doing. It's just
okay.
that it's dehumidifying the ventilation air.
Okay.
It just became a central system. No, it's just a discharge sensor, and you have to rely on setbacks you have to rely on temperature change. So the toughest part about the way that those systems operate is that what temperature do they want to discharge at? How do they decide that? And usually it's like a pre-programmed thing to decide that, and that's actually what we modeled. But if you were able to actually adaptively control that based on how the building was operating, and if the DOAS somehow knew if everybody was in cooling or if everybody was in heating, and then say if the whole building's in heating, it just knows to give it as much heat as it can, because it's got a really efficient compressor, take the load off of all the units inside, and say that everything's in cooling, it would just give you 52-degree air. But that's not how they're typically controlled. They're typically controlled on an outdoor air temperature reset. So they have like it's an arbitrary temperature that they flip the temperature. So they're in heating, when it's 0 out, they go as high as they can, and then at 55 degrees, all of a sudden they flip, and they go from 80 down to 55, just kind of arbitrarily at one point. And there is definitely some optimization that needs to be done in that field of controls. If you have all these sophisticated control systems, if they're talking to each other, they can be even more efficient.
We hope to see you again next week, if not before. Thank you, everyone, for coming. Good night.